Hi everybody, I'm honored to be here. Thankful you guys gave me this opportunity to wear my suit. This is our project, feasibility study of rocket recovery using a drone guided by GPS signal and computer vision. My name is Micah, Pham, I'm an aerospace engineering student, and this is Nguyen, she's a computer science major. Really a cross-department project going on. Yeah. Cool, we are mentored by Dr. Angelo Esposito. Sorry. This is I like to note that this is a simulation. We are able to verify that this is feasible and that from the simulation data, we can see the performance requirement of all of the drone and rocket. So when I go build this in reality, I can have a comprehensive part list. Play the video. You did red would be the rocket and blue would be the drone. It's falling. And now drone is tracing after that white dot right there, you can see it. Now drone is tracing after the actual rocket, and we stop before we hit the ground. There's two altitude levels that are quite important. 400 feet AGL above ground level would be the level that drones have to fly under the ceiling for all drone operating in the United States. Our drone went up to 4,000. This is normal operation. In order to go up to 4,000, we need to apply for a waiver, and it requires more stringent requirements, and you have to have more equipment, and you have to operate in a safe space for that. Cool. Let's go over some background on rocket recovery. When you first think of this word, you typically would think about SpaceX. Picture right here, what we would call this is propulsive landing. And since 2009, their first landing, many companies follow them. These include Blue Origin, Silk Space, Relativity Space, Rocket Lab, just to name a few. And in 2023, they started a colligated lander challenge with the top prize being $50,000. But these rockets, they would require cryogenically cool liquid propellant. Liquid propellant, it's more suitable for this because it's a liquid. You can vary how much fuel you go into the engine by a valve. But it is very lengthy and expensive to develop. The fluid line, the valve, the engine, they have to be able to withstand extreme temperature and extreme temperature swing. They're going to really cold to really hot, so that's going to be very pricey. And here at OCC, we only keep students for 2 to 3 years, so we have a workforce. That have a constant brain drain going on, so this is not very suitable for us. So here's what we're doing instead. We're doing mid-air recovery. It's an old idea brought back by the Rocket Lab. It came all the way back from Cold War reconnaissance. It's really interesting history, so if you want to know, ask me about it later. Questions? Fine. It's abandoned after 2 failed attempts for flight food safety. They lost telemetry data and it was inclement weather. They couldn't see visually verify where the location of the rocket is. When you're flying a helicopter in a place where there's a falling rocket from the sky, it's quite dangerous because for all you know, it could be right above the rotor disc. That's going to be a bad day at the office, right? So this is more suitable for the OCC. We're using typical solid fuel high power rocket. Amateur rocket are required to have a parachute by regulation. And also we're using drone with off-the-shelf component. We're integrating system, we're not building everything. The project goal, how we're deviating from this is instead of using a helicopter, we're using an autonomous vehicle to mitigate the risk of human life. 2 major components. We're using GPS-based guidance and computer vision. GPS-based guidance will be used when the 2 vehicles are apart. And then when the vehicle gets closer, we will be using computer vision for the precise maneuver that's needed to catch the rocket. For GPS-based guidance, we're using pursuit curve. It is a branch of mathematics that involves differential equations, and we're using a part that's called pure pursuit. We're doing no lead to lag, and we're borrowing idea from it. We're basically pointing the derivative to where the rocket is, And yeah. So, and proportional navigation will be implemented in the future. This is work in satellites and missile interception and all that. Yeah. Another thing that we need is velocity controller. When the drone and the rocket gets too close to each other, we need to be able to pull back on the throttle and give them some distance. Computer vision is another part of our project. It's involved AI, it's all the rage these days. And for hardware, using Arduino Micah, and yeah, it's a low power PCB with a camera on. Let's go over the vehicle. For a rocket, we need to achieve as high altitude as possible. In aviation, there's a saying is that altitude is time before you hit the ground. And to do that, we need a minimum diameter to sort of minimize the frontal area, less drag. We need a big parachute, land softly, slowly through the air. And it's designed and simulated using open rocket and all that data reported over to MATLAB for further analysis. Vehicle, drone, we're using an off-the-shelf motor. That's the link for the product. So I have two targets. The top chart up here is to verify that the drone can hold the rocket, hold the weight of the rocket, right? And not operate at so much power that the motor will burn up. That's what this red line separates. The unit power and intermittent power. This one is the vertical thrust you have at different pitch angle. So when you're pitching, some of the thrust goes this way, and some of it goes this way. We want to make sure that we can maneuver but still staying at an altitude. All of this was learned from physics mechanics with Dr. Guerra. And it's inspired by aviation performance chart. I started school here at OCC with the aviation maintenance technician program, so I'm really going back to my roots. I always wonder how they make these things. And what is all this? What are these charts? What is that animation you saw earlier? Well, what I would describe it as is a very elaborate piece of napkin math, basically. It's a 300 line code. Some low fidelity simulation, 2 dimension. A lot of the physics was neglected for this animation because we're just trying to design a control loop. It's not very resistant to noise. When I say noise, what it is for our project is wind. Wind is not constant. It doesn't come from the same direction at the same force. It varies in direction, and then you get low wind and high wind all of a sudden. That's what we call gust, right? It's tuned for a very specific flight path of the rocket. If it's on a denser day where the air is thick and soupy, rocket won't go as high, and then this is all not optimized anymore. I have to change certain parameters to get it working again. It's just built to understand flight profile, what are the bases that we have, and it's just to validate available catch windows, right? And our catch window is 4 minutes and 20 seconds. That gives us about 3 catch attempts depending on how quickly we can reset after that time. Also, it looks cool. A picture is worth 1,000,000 words, and that animation is about 1,000 pictures played back to back. But yeah, it's a 1,000,000-word essay you're looking at. Cool. Earlier. Here's V to tell you about computer vision.
Hello everybody, I'm V and I'm responsible for the computer vision part of this project. Computer vision is a subfield of artificial intelligence and computer science that teaches the computer how to interpret visual data that it receives. Now, in order to accomplish this goal for our project specifically, we utilize Edge Impulse, which is an online platform that allows you to simplify the process of creating, training, and deploying machine learning models capable of object detection. And in order to create the model, we took a lot of pictures of the object that we want to identify and then labeling what the object actually is. And in our case, it's the parachute, as you can see in the picture right here. And then the training part of it is taken over by Edge Impulse. Once it's done training, it gives us back some useful information like an F1 score, you can see out there, or an overall performance score. And basically what an F1 score is it's a number that indicates a balance between precision and recall. And recall is a number of true positives that the model was able to identify correctly during training. Now, after training, all that's left to do is deploying the actual model onto the board itself to be used. And this, and then OpenMV comes in during this part to act as a middleman to translate the information that the board sees with its camera to the actual model. And it will give us back some useful information like precision score and where the object was identified. These information can be used later on to further improve the project in the future. Everything that I just explained can really be simply understood as edge impulse being the brain, OpenMV being the nervous system, and the body being the board itself. And this is the final product of computer vision. All three of the technologies that I've listed earlier working together to identify that a parachute is actually a parachute.
So, what we've been talking about, low fidelity approximation to reality, here is an analogy. This is a fully drawn drawing of me sitting on a lawn chair in the back of a pickup truck holding a fishing rod with a parachute attached on the fishing line and a drone flying above my head. Today you're getting this, and tomorrow, someday, maybe you get a picture one day. So one detail I can point out is that the parachute is a different color. Trying to find a yellow parachute in the middle of the desert, it's like finding a specific piece of hay in a haystack. That's not going to work out for anybody, right? So that's the actual last slide. So in the future, we'll be using a different program similar to MATLAB. It's like a sister program where you have signal coming into a block, signal being an input, and it goes output to another block. It is how control system are typically think of when you look at textbooks and stuff like that. And then we can take all of that and then put all that data into a program called Unreal Engine that is used by game developer to make virtual spaces. And then we can actually train the computer vision stuff that we have with a virtual parachute in a virtual space to teach it to recognize stuff. That's how Tesla supplement the real life data with by using virtual environment to train the cars. And moving forward in this project, this is somewhat of a timeline. Going in the future, will be, if we have enough interest in this project, I run a Broad Street Club, so if we have enough people, we can split out into teams and do things in parallel. We'll be developing all of this stuff in parallel, building the drone and getting certification and waivers from the FAA. Yeah, and then hopefully one day it can happen. And this is called modeling like a aircraft certification program. So yeah, it's exciting going forward.
Does anyone have any questions for them about their presentation?
So you mentioned that you're going back to a process of these rockets from the past that then is no longer being used, is that right?
I'm sorry.
So the history of this other...
No, I'm glad you asked. It just so happened I have a slide just for that.
You're welcome.
No, yeah. The catch and latch mechanism, this is fun stuff. This is from Cold War reconnaissance. Back then they have film camera and then wireless communication isn't all like now it is now. So they have these like film pods and they took a picture of the Soviet Union and they need to get it back to an analyst in America. So what they would do is they drop down these like film pod and then a plane would come and swoop it up. So this is like old stuff. We have the example in Corona spy satellite. If you guys know, you know aviation history, you know the SR-71. and it has this little brother drone, the Rocky P-21. You play Battlefield, there's like a scene where people are getting picked up by like a C-130 on the ground. So yeah, this is like, there's a lot of history about it. And this is something that I won't be handling personally in the future. And it's an open up research opportunity for any CARL member. It's a Coast Aeronautic Astronautical Research Lab. Yeah. And one thing I can tell you right now is that all these lines have to be somewhat elastic. When you catch it, you would want to dampen out the force impulse that you have, or that if there's wind blowing, you can dampen that out, force out. So I like to connect what they're learning with like what they're doing. It's really important for me. That's it. So, yeah. Cool.
Thank you.
Yeah.
Any other questions? No? Okay. Questions? No? Okay, well, thank you so much. That was